Welcome to the fourth lecture in our series on quantum mechanics. In today's lecture, we will talk about the mathematical basis or the mathematical foundations of quantum mechanics. This is the first part of a series of lectures in which we will talk about the mathematical foundations or the mathematical background needed to understand quantum mechanics. We will start with a little review of probability density and applying it to discrete and continuous systems. We will then talk about the wave function, and we have talked about it briefly in earlier lectures, but now we will give a formal definition to the wave function. We will then associate wave function with the idea of probabilities. We will then talk about a very important concept called normalization. We will then discuss vector spaces and Hilbert spaces. This is a part of linear algebra. Then we will talk about Dirac's Bra-Ket notation, which is very commonly used in quantum mechanics. And we will end our lecture with some examples. Let's start with the concept of probability density and applying it to discrete and continuous systems. So in the discrete case, let's take the case of 10 coins. 2 are of value of 10, 3 are of value 20, 4 are of value 50, and 1 is of value 100. Now, if somebody asks us, what is the probability of getting a coin of value 10 if we randomly picked a coin from this set of 10 coins? Of course, we know that the 2 coins of value 10. So the probability of picking a value 10 coin is 2 by 10. And 10 is the total number of coins. And 2 is the number of coins of the desired value. We write it like this. Now, we know that the sum of all the probabilities here should add up to 1. Because if we are picking up a coin, then we will get some coin of some value. So, the probability of picking up value 10 coins is 2 by 10. Probability of picking up value 20 coins is 3 by 10. The probability of picking up coin of 50 value is 4 by 10. The probability of picking up a coin of value 100 is 1 by 10. And it all adds up to 10 by 10 equals 1. So the sum of probabilities equals 1. So we express that as Ni upon n equals 1, where Ni is number of coins of a certain value and n is the total number of coins. Now what is the average value of this set? The average value is given by the value of the coin multiplied by probability of that coin. So here is the value and this is the probability. So we can see this as 2 by 10 into 10 plus 3 by 10 into 20 plus 4 by 10 into 50 plus 5 by 10 into 100. This is very easy to see because an average is just the sum of all values divided by the total number. For example, if one were to calculate the average of this set, it is nothing but 10 plus 10 plus 20 plus 20 plus 20 plus 50 into 4 times plus 100 divided by the total number, that is 10. And this is what we get over here. So the way to write this is the value into the probability of that value and a summation of that. Now, all this is very easy to understand in the discrete case. Now, let's extend this to a continuous system. So, by continuous, we mean that the values are not fixed numbers or whole numbers. Let's take an example. Let's say we have a ball and the ball can go anywhere on the x-axis. There is a wall at a point A and another wall at the point B. The ball can exist anywhere between A to B. So, there is a probability of the ball being at different places. Here, Px we define as the probability density of the ball in the system. What that means is that Px dx is the probability of the ball being found between x and x plus dx. So, Px is the probability density and Px dx is the probability of the ball between x and x plus dx. And if you integrate this from the minimum possible value to the maximum possible value, that is a and b, you should get a 1. Sum of probabilities again have to be 1. So this is the sum of probabilities equation for the discrete case, and this is the sum of probabilities equation for the continuous case, and these two are basically related. In the continuous case, we needed the concept of probability density and we needed the integral. In the discrete case, it was a summation. Similarly, similar to this formula, we also have an average value. So the average value of the x position is given by this. We multiply the x position by the probability density into dx between a and b. So this is the counterpart of this one. Again, in this case, we needed the summation. We did not need the integral. In the continuous case, we need the integral. But the basic idea is the same. You can extend this concept and find the average of any function of x in the system. So the average of any function of x, and you write it like this, is instead of x, you multiply by fx, the probability density, and the dx from a to b. So if you know the probability density, it's very easy to find the average of any function of x in that system. Now we will use this concept in our study of quantum mechanics. The most important thing in quantum mechanics is the wave function. The wave function describes the quantum system or the quantum particle. So if you know the wave function of a system, you know everything about the system. And this is how you represent it. So this is just shorter way to represent it. This explicitly tells us it's a function of x and t. Of course, it could also be a function of x, y, z, and t. This is also a wave function for which there is a dependence on 3 coordinates and time. The wave function in general is complex valued. The complex numbers are needed in our current mathematical understanding of quantum mechanics. So to define the wave function is a complex valued probability amplitude of a system. So what that means is the square of the wave function is the probability density. We talked about probability density in our previous slide. So the square of the wave function is the probability density. The wave function itself is the probability amplitude, and it is complex valued. So since the square of the wave function is the probability density, so this is the probability density multiplied by dx from a to b gives us the probability that the particle is found between a and b. This is very similar to the concept we studied in the last slide. So this is how the wave function is related to probabilities. So our understanding of a quantum system is of a probabilistic nature. We can only know the probabilities of a particle being found at certain places, and the square of the wave function gives us the probabilities. Now, on the last slide, we understood that the square of the wave function multiplied by dx and integrated gives us the probability of finding the particle between points A and B. But now, if you're talking about a particle, then it must be found somewhere. Particle has to exist. That leads us to the normalization condition that the probability of finding the particle between minus infinity and plus infinity has to be equal to 1. So this is the square of the wave function, which is the probability density, into dx from minus infinity to infinity has to be equal to 1. What this means is that the particle has to be found somewhere between minus infinity and infinity. All sensible wave functions must be normalized. So if you find a wave function that is not normalized, you can reject that wave function because it makes no sense in quantum mechanics. One hears the word square integrable many times. What this means is that if a function fx, the square of that dx, is less than infinity, that means it does not blow up. This integral does not blow up. This integral is a number smaller than infinity. Then this means that fx is a square integrable function. So applying this to our case of quantum mechanics, our wave function, of course, is square integrable, because if you take the integral of the square of that between minus infinity to infinity, this is less than infinity. So our wave function is square integrable, but the stronger condition that we impose upon it is that it is normalized. That is, the integral is equal to 1. This condition we have studied in our earlier case of coins and ball just tells you that the sum of the probabilities has to be equal to 1. Normalization is an important characteristic of any valid wave function in quantum mechanics. Now let's talk about a very useful and important concept, that is vector spaces. The subject of linear algebra deals with the concept of vector spaces. And vector spaces are very important in quantum mechanics. A linear vector space, that is V, consists of vectors represented in Greek letters here and scalars represented in English alphabet here, obeying the following properties. So these are the properties: addition properties and multiplication properties, which a linear vector space must have. Typically, when we talk about the concept of vectors, we think of what we have learned in high school, that is force vector or the momentum vector. Think of this as an extension of that concept, and we will try to relate these concepts to that as well. But let's look at the properties that a linear vector space must have. So addition rules. Commutativity, that is, if there are two vectors, they can be added either ways. It makes no difference. Associativity. So if you have three vectors and you're adding them together, does not matter which two you add first. So this is the concept of associativity. Then in vector addition, there exists an identity such that, so this is a zero vector which added to any vector will yield that vector itself. So here's the concept of identity comes in. Then you have concept of inverse of vector. That is, for every vector, there exists its inverse, and when they add together, they produce the zero vector, which we just studied about here. And then we have the concept of closure. That is, if this vector is a part of this vector space, and this vector is also a part of this vector space, then adding them together will also be in that same vector space. So you can add two vectors and you stay within the vector space that you started off with. That's a concept of closure. Similarly, you have some multiplication rules. Distributivity, that is, if you have a scalar multiplying the sum of two vectors, then you can distribute them like this. And then you have the concept of associativity. So if you have two scalars multiplying a vector, then whether you multiply b with that vector first, or you multiply the two scalars first and then multiply with that vector, does not matter. Both will give the same result. Then you have the concept of identity. There exists a scalar, the unit scalar, which multiplied by any vector will bring back the same vector. Note that this is a scalar. Note that we have not defined any way of multiplying two vectors yet. We will talk about that concept, but till now we have only multiplied scalars with vectors. Then you have the concept of closure. So multiplying a scalar with a vector, which is an element of a vector space, the result will also remain an element of the same vector space. So you cannot go out of that vector space by multiplying a vector with a scalar. So these are the rules which a vector space must have for it to be a valid vector space. Another rule that we must state here is there's a commutativity in multiplication as well. So this is same as in which this is the vector and this is the scalar. So now let's talk about Hilbert spaces. So Hilbert spaces are a special kind of vector spaces. So Hilbert space is a linear vector space. And why this is important to understand is because quantum mechanics wave functions, they exist in Hilbert spaces. So Hilbert spaces are needed to describe our wave functions. The additional concept that a Hilbert space must have over the rules that we studied in the previous slide is that they must have an inner product. In the last slide, we had not defined a way to multiply two vectors. Now we do. We call it the inner product or the scalar product. We call it the scalar product because the result of that multiplication is a scalar. And this is how you multiply two vectors in a Hilbert space. So we write the inner product as something like this, and this is what it results in. It's an integral in which one of the vectors find itself in a complex conjugate form and the other one as it is, and you integrate over all of space, and this is what the inner product looks like. So any vector space which has got an inner product, we can call that a Hilbert space, and in quantum mechanics we will deal with Hilbert spaces. Another important concept that we come across is that of linear independence. So if you have a Hilbert space with vectors like, let's say you have 3 vectors in the Hilbert space and you multiply them by some scalar and the result is 0. If a1 equal to 0, a2 equal to 0 and a3 equal to 0, then these 3 vectors phi1, phi2 and phi3 are called linearly independent. So if the sum of such terms is 0 and if it implies that all of ai's are 0, then the collection of these vectors is said to be linearly independent. That means these cannot be expressed in terms of one another. If all these ai's are not 0, that means one of these vectors can be expressed as a linear expansion of the others. That implies that those vectors are linearly dependent. Now let's talk about basis vectors. And here the concept of linear independence comes in. The maximum number of linear independent vectors in a space, we call them basis vectors. And any vector in the space can be expressed as a linear combination of the basis vectors. So basis vectors have a special importance. They cannot be expressed in terms of each other because they're linearly independent, but other vectors can be expressed as a linear combination of basis vectors. The choice of basis vectors is arbitrary. So if you have a collection of basis vectors, you can choose any one of them as long as they satisfy certain conditions. But it's convenient to choose orthonormal basis vectors. By orthonormal, we mean that let's say you have one basis vector and the other basis vector as phi2. Then if that is the inner product is 0, and if the inner product of these with themselves is 1, then we call them orthonormal basis vectors. And we prefer such kind of basis vectors to describe any quantum state. The number of basis vectors in a certain space is called the dimension of the space. Now here we can relate all this to vectors that we have learned in high school. So let's say we had a certain force and this is a vector and we could express that as, so this force vector is being expressed in terms of these basis vectors. These are the basis vectors, the I, J, K's here. So I, J, K are the basis vectors of Euclidean space. Now they are orthonormal because here we see the same orthonormality condition that we saw here. And in Euclidean space, the dot product is our inner product or scalar product. So if we had two vectors, f1 and f2, the dot product yields a scalar, and this is our scalar product or inner product for Euclidean space. The number of basis vectors is called the dimension of a space, and we see it as an example for Euclidean space where the number of basis vectors is 3, so we say it's a 3-dimensional space. So to summarize, we had defined vector spaces in the previous slide. In this slide, we added the concept of inner product or scalar product and defined linear independence. That is, a set of vectors is said to be linearly independent if they cannot be expressed as a combination of others. And basis vectors are the maximum number of linearly independent vectors of a space. And we related these concepts to the concept of vectors that we studied in high school, which is the Euclidean vector space, in which the number of basis vectors is 3. Let's now talk about the Dirac notation. The Dirac notation is a very useful concept which helps us write the equations of quantum mechanics very easily. We already saw it. So we saw in the last slide that the inner product of two vectors is given by this. In defining the inner product, we already used the Dirac notation. So this part is called the Bra and this part is called the Ket. The Ket is a vector in a vector space V. Of course, it could be V or U or whatever, but it is a vector in a vector space. We call it V here. The Bra is a vector in a dual vector space. Let's call it V star. So these two are not vectors in the same space. They are vectors in, this guy is a vector in space V and the Bra is a vector in the dual space. So the Bra and the Ket notation is what Dirac introduced. Let's talk a little bit about the properties of Bras and Kets. So here we have this scalar multiplied by this vector. You can bring the scalar out of the Ket. Here also we see the scalar inside the Bra. You can bring out the scalar here, but it has to be a complex conjugate. Here we see the inner product. The complex conjugate of this inner product lets you reverse the Bra and the Ket. So as we studied in the last slide, this is the inner product and it's a scalar. So you can reverse it in terms of Bra and Ket, but you have to make it a complex conjugate. Next we come to the Cauchy-Schwarz inequality, which states that the square of this inner product is less than equal to these two inner products, basically the psi multiplied by psi and the phi multiplied by the phi. So this is called the norm of a vector. This is called the norm of this vector. So the norm of the phi vector and the psi vector is greater than equal to the inner product of phi and the psi squared. In the last slide, we had talked about orthonormal basis vectors. So two vectors, Fm and Fn, are said to be orthonormal if the product is this number. It's called the Kronecker delta. Now this 1 or 0 if m equal to n, if m is not equal to n. So let's take the example. Let's take, say we have two vectors, phi1 and phi2, and one vector multiplied by the other vector in terms of the inner product gives us a 0 and multiplied by itself gives us a 1. Then they're said to be orthonormal vectors. In the last slide, we said that the basis vectors are typically chosen to be orthonormal vectors. Now, just as in the last slide, we had expanded force in terms of these three basis vectors I, j and k in Euclidean space. In quantum mechanics also, you can expand any vector into a linear combination of the basis vectors. So these are basis vectors. So let's say you had three basis vectors. So any vector can be written as a linear combination of the three basis vectors, phi1, phi2 and phi3. Now, the a1, a2 and a3 are three scalars which we need to determine. An easy way of determining this a1, a2, a3 is to multiply, let's say, by phi1 on both sides. Now, this term becomes something of this sort. You can bring out the a2 and this becomes 0 because the phi1 and phi2 are orthonormal. So this guy vanishes and this guy also vanishes. We are left with this guy and this guy becomes a1. This is how you determine a1, by multiplying this vector for which we did the expansion by one of the basis vectors. Now we learned about the Bra and the Ket. What is the interpretation of this? Let's now return back to Euclidean space and try to form an association. Let's say you had two vectors a and b, and in Euclidean space the a dot b is the inner product. Let's say this is a and this is b. So a dot b, which is the inner product, is just ab cos theta. It is just a multiplied by the projection of b along a. That's what a dot b is. Similarly, you can say that this notation, this inner product, is just the multiplication of the projection of this vector along this vector. Another way of looking at it is that this is a probability amplitude. When you measure this vector, the probability of it being found in this state after measurement is the square of this. So this guy, which is our inner product, is a probability amplitude. Now in quantum mechanics, you can have discrete basis vectors or continuous basis vectors. A remark that we want to make here is that when we're talking about discrete basis vectors, ket is a column vector. So this ket would be something of this sort, and a bra would be a row vector. So this associates our bra and ket with matrices, and we will use it to solve problems on the next slide. Let's now do an example. So this example I have taken from a book on quantum mechanics by Zitelli. So we have two kets, and as we saw in the previous slide, a ket is a column matrix. We need to find complex conjugate of one of the kets. The complex conjugate is simple. It would be, so now we need to find the bra corresponding to this ket. In order to do that, we need to first find the complex conjugate of the ket and then convert the column matrix into a row matrix. So all we need to do this is to convert the column into rows. So this is the bra that corresponds to this ket. Now the question is this ket normalized? And if not, normalize it. For this we need to find this inner product. If this is 1, then it is normalized. If not, it is not normalized. And then we need to normalize it. Let's see what this is. We have already found the bra and we have been given the ket. So all we need to do to find this is do this multiplication. And what we will see here is that we get 30. Remember that this inner product is always going to be a scalar. It is not a vector, so it's not a bra or a ket. It has to be a scalar. So this means, since it is not 1, this means that it is not normalized. In order to normalize it, we need to write the ket as follows. Similarly, the bra would be written as follows. Now, of course, this is not the same bra or the ket, so let's put a prime there just to distinguish between this new ket, which is normalized, and this one, the original ket, which is not normalized. Now, if you find the inner product, you should get this. And thus we have normalized our ket. Now, are the two kets orthogonal? He's asking us whether this ket and this ket are orthogonal or not. Let's create some space for ourselves to do this. What we need to show is this equal to 0. If this is 0, then it is orthogonal. If it is not 0, then these are not orthogonal. But first we need to find the bra corresponding to this ket. And we can easily see that that would be the technique as we described here is simple. Take the complex conjugate and convert the column vector into a row vector, or the column matrix into a row matrix. In order to find the inner product, we just need to multiply these two together in terms of matrix multiplication. And we will see that the answer is, and since this is not equal to 0, these two kets are not orthogonal to each other. Now let's look at another example. This example I have taken from the book on quantum mechanics by Griffiths. Consider a three-dimensional vector space spanned by orthonormal bases, kets 1, 2, and 3. So this means that these three kets are the orthonormal bases for this three-dimensional vector space. What this means is that the inner product of 1 with itself, the bra and the ket, is going to be 1, or in other words, the norm of 1 is 1. Similarly, however, this is the normality condition or normalization condition. Orthogonality condition is etc. So this sums up what we mean by the orthonormal basis. This also means that any ket can be expressed in terms of this orthonormal basis 1, 2, and 3. So we have two kets here, alpha and beta, and alpha has been expressed in terms of this basis and so has been beta. these two kets, alpha and beta, these are not basis kets. They are expressed in terms of these bases. Now we have to construct the bra of alpha, the bra of beta in terms of the base kets 1, 2 and 3. So alpha, the bra, we just have to take this ket alpha and change the kets into the bras, but also do a complex conjugate. So this would be minus iota. Similarly, the bra of beta would be, so this is how we construct the bra of alpha and the bra of beta from the ket of alpha and ket of beta. We basically turn all these base kets 1, 2 and 3 into their base bras 1, 2 and 3, and we take the complex conjugate. Wherever we find iota, we make that minus iota. Now we have to see what this inner product is. So let's find this inner product. For this we have to multiply with, so this is the bra of alpha, we multiply it by ket of beta. When we calculate this, remember these conditions here, these orthonormality conditions. So the inner product of bra of 1 and the ket of 1 will give us 1. The inner product of the bra of 1 and the ket of 3 will give us 0. So all we need to do is multiply the bra of 1 with the ket of 1, which gives us 1. We don't need to bother about the bra of 2 because it multiplies with the ket of 1 or the ket of 3 and becomes 0. This guy, the bra of 3, gets multiplied with the ket of 3 and becomes plus 2 iota. Similarly, we can calculate this inner product, which is the bra of beta, which we had calculated here, and the ket of alpha. The ket of alpha was given to us in our question statement. Here also, we only need to calculate the inner product of 1 bra with 1 ket and bra of 3 with the ket of 3. All other terms will vanish based on the orthonormality condition. So what we get here is, so indeed we have shown here is that the inner product of the bra of alpha, the ket of beta, is a complex conjugate of the inner product of the bra of beta and the ket of alpha, because this guy and this guy here are complex conjugates of each other. So this ends our 4th lecture in quantum mechanics, and this was the first of a series of lectures in which we will talk about the mathematical basis of quantum mechanics. In the next lecture, we will continue to talk about the mathematical structure of quantum mechanics and the foundation we need to understand quantum mechanics. Thank you.